For problem number 19, it says use the right-hand rule, force rule, to find the direction of the current in the wire shown in figure 19.36. In each case, the magnetic force direction is shown. In each case, the wire is a straight segment 1.7. Okay, so that's part B. So let's do part A first. And part B says in each case, the wire is a straight segment 15 centimeters long, carrying a current of 5.5 amps. And in the B field, or magnetic field, whose strength is 1 millitesla, determine the magnitude of the magnetic force. All right, so let's do part A. So basically what we're going to do is we're going to use this right-hand rule to determine the direction of the current. So what you want to do is you want to point your fingertips in the direction of the magnetic field and the palm of your hand in the direction of the force. So if I do that, my palm will be facing out from the board, and my fingertips, so my hand, I'm going to draw what my hand would look like. My hand looks like this, and my thumb is pointing that way. So for the first one, we would say to the right. So the current is what we're looking for. So the current, and I'll draw that in green, will go to the right. On the next one, I'm going to point my fingertips in the direction of these blue lines. Okay, so I'm going to point my fingertips in this direction. And then the force, the palm of my hand, is going to face into the board, because that's what that means. And so if I draw my hand, when I do that, I'm going to get my thumb like this. Okay, so that means that my current, in this particular case, will be going up. So this one goes to the right, this one goes upward. In the third situation, I'm going to take my hand and I'm going to have my fingertips pointing upward. Okay, so my fingertips are pointing upward. The palm of my hand, this is going to be kind of hard, the palm of my hand is facing the same direction of the force, so my thumb is actually pointing into the board. So I can't really see the current, but what it's doing is it's going into the board. So you would draw that like this, and then in parentheses you would say into the board, all right, or into the page. So we're doing good so far. I guess I could draw it. It would just kind of look like you couldn't see my thumb really, but you'd see my fingers. My hand's kind of sideways if you do it that way. So now let's do the fourth situation. I'm going to point my fingers in towards the board, and my palm is facing down, so the current then would go left. And then lastly, I'm going to point my fingers away from the board with no force. Now that one is kind of a trick question. So if my fingers are going this way, I suppose my thumb could go to the left, or it could, well wait, let me think about that. My fingers are going, no, away from the board, and there's no force. So if force equals 0, I think this would be either into or out of the page. Yeah. This is a special case. Okay. So now for part B, it says in each case, the wire is a straight segment of 15 centimeters long, carrying a current of 5.5 amps, and the magnetic field strength is 1 millitesla, determine the magnitude of the magnetic force. Okay, so now that's easy. That's the math. So all of the cases look to be the same except for the fifth case. So for part B, remember that the relationship, the force is always equal to the current times the length of the wire times the magnitude of the magnetic field times sine of theta. Okay? And so all of the cases except for V, so case I through IV, theta will always equal 90 degrees, right? Because that's what the right-hand thumb rule means. So the force and the magnetic field are both 90 degrees from the current, okay? So now I just got to plug and chug. So now the current we said was 5.5 amps, right? Now the length was given to us in centimeters, so we got to convert that to meters, and that would be 0.15. Tesla was millitesla, so we got to convert that, so that'd be 1.0 times 10 to the negative 3 Tesla. And then sine of 90. All right, which I think is 1 if I remember correctly. So now, to calculate that, if I plug all that in my calculator, I get 8.3 times 10.3 times 10 to the negative 4 newtons, all right? And then if for case number 5, if I do this for case number 5, in this particular case, for case number 5 or V, theta would then be equal to 0 degrees. And remember, according to your unit circle, on the unit circle we have cosine, comma sine, and 90 degrees is up here. And so on the unit circle this is 0, comma 1, but over here this is 1, comma 0. So this is 0 degrees here. So what I'm saying is that sine of 0 degrees is 0. So then my force would be ILB times the quantity 0 or just 0. Okay? Does that make sense?